When I started making video games, the first thing I fell in love with was level design. I really loved piecing together levels to create entire worlds, but I quickly ran into problems. When I individually placed things and tried to attach and align them together, it would just not work. Even with the copy-paste functions, I was spending so much time fiddling with placement, rotations, trying to lock things together. And that's when I knew there had to be a better way. I ended up discovering two techniques of placing meshes that changed the way I make levels. It saved me hundreds of hours and even increased the performance, and I'm excited to share this with you today. So let's jump in. So let's go to the first one. The first one is the regular spline mesh. So this tube here is a regular spline mesh. It uses Spline Mesh Component. We'll look at the blueprint after. And as you can see, when I move the tangent, I can cause deformation. I can also trigger a random coloring, which happens every time I move or add sections. In terms of LODs, we can see that each individual object has its own LOD. See, we have 1, 2, 3 exclamation marks, and then we're missing the dot. And then you can't really see it further, but there's deformation. And in fact, the whole exclamation mark disappears. So let's take a look at how it works. So everything is done in the construction script. All you need to do is add a spline itself. And well, let's go through it. The first part here is set the section length. So the section length will define in a length of the spline how much of it is a section for your mesh. The reason we create this is to only create meshes if the spline is extended past that threshold of the section length. So here, if I go back to my tube, I can extend this, but as long as I don't pass the section length threshold, it won't appear. That's because I want to add to it. I don't want to deform or stretch out an existing section. So here we just get the actor scale 3D. We're looking at the x-axis, and we're going to get something called the section length coefficient, which will be calculated later when we define what the spline mesh component is. And then we set it up. Afterward, we're going to calculate the length of the spline divided by the section length to determine if it adds a mesh or not. So this is how we do it. Get the spline, get the length, divided by the section length, truncate it, and -1, of course. And we will, because we're using indexes or indices, and then we're going to go for a for loop. So each time we add something, it's rerunning this operation in the construction script. Okay. So here's a little bit of code I had to put in. I put a switch based on an integer for one mesh or another. Unfortunately, I have not figured out if there's an easier way to assign the spline mesh component mesh other than hard coding it, but this seems to work fine. You can make your switch as big as you want, you can make it into an array, etc. You can actually make this into a more complex function. If it's 0, it's a crate. If it's 1, it's a pipe. Once we defined what our mesh component is, and we added it, so add the block, make sure that the forward axis is in the X direction, and set up more defaults. We can then use this calculation here, which is get the spline mesh component, get the static mesh out of it, get the bounding box from the static mesh, and then measure the minimum and maximum X values, find the difference, and set the section length coefficient to it. Make sure that you subtract from the maximum the minimum. Afterwards, you no longer have to manually set this variable, it will auto set itself. Here is a little bit more complex. Spline meshes, unfortunately, the component needs more definitions than just adding it. It needs to know, okay, where's my beginning, where's my end, how far is my tangent, what do I do with all this? And this is basically how it all gets defined here. I could go through it, but it is exceedingly long and does not actually add any value to this tutorial. And then finally, once you've defined your static mesh component, you can actually change values off of it. Set the collision, the collision channels, the color scheme, and then set the material from the color scheme. Here I just made a quick switch based on a enumerable, where based on the selection, pick either yellow, green, blue, red, pink, or random. And then output the material. And that's what you get. The next one we're going to look at is the hierarchical instance mesh. It basically builds the hierarchical static meshes on top of the spline or following the spline. Now, as you can clearly see, there's an issue here with the deformation. It does not deform as intended. So that's going to be a drawback. So if you need deformation like in pipes, you're not going to be able to achieve it here. Another issue is, although you can change all the colors, you cannot change random individual colors. And finally, the LODs. As you can see, each one of them has its own individual LOD. Let's take a quick look at the blueprint. Again, here I actually managed to set the static mesh in the beginning and making it into a public variable. So when you bring your hierarchical static mesh actor into the scene, you see it's empty, but then we can assign whatever we want to it, and it will just change to that. Change your mind, change it for something else. Once we've set that up, again, get the section length coefficient. But since we already defined the static mesh here, we don't need to do it later, we can do it earlier. And then define the section length. Once we have our section length, divide the spline by the section length. And then for each of those dividends, we're going to do a for loop. We're going to add to it. So notice I have a spline and I have a hierarchical instance mesh component. We're going to take that same component and just add an instance to it. And we're going to add it at, so here we don't actually have to define the beginning, ends, or anything else. We can just define the transform. Get the location along the spline. Easy enough, you can just multiply the current index with the section length and you'll know exactly what position it should be at. Make that the new transform. And here I've added a miscellaneous color scheme function to change the color. And that's it. The final one we will look at is the instanced mesh. So the first thing you'll notice is that the LODs are consistent across the entire object. There's no individual LODs. And that's one of the drawbacks of the instanced mesh. There is nothing else to add to this explanation. It is the exact same blueprint as with the hierarchical one, with the exception that it's going to use the instanced static mesh component instead of the hierarchical instanced static mesh component, and everything else is exactly the same. So this is all great. We kind of see what some drawbacks are for some and what some advantages are for others. So for the spline, you can force deformation, you can have individual properties, whereas for the hierarchical instance mesh, you can't, but it does hold individual LOD properties, whereas the instance static mesh does not do any of that. It just makes the thing. So now we're going to take a look at performance. So again, tilde stat scene render and tilde stat units, sorry. Let's get the FPS also. So at rest we have about 120 FPS, 8 milliseconds each. The mesh draw call is at about 11. If we turn around and we look at this beautiful scenario, the draw call spikes to 180 and our frames per second drop to about 60. The draw thread, which is on the CPU, is bottlenecked, not the GPU. The reason that the GPU is high is because it is synced to the frame time. But the real issue is the draw thread. If we improve that by reducing draw calls, the GPU will follow. Now let's compare the hierarchical instanced mesh. So again, at rest, we have the same values as before, 120 FPS, mesh draws 11, and then we look at this beautiful thing. Mesh draws only go up to 23, and we're still maintaining 100 to 110 frames per second. The results are very encouraging. And due to the deformation, we're also allowing the system to work much better. Finally, we have the ISM, or the Instanced Static Mesh. Here we can see we are saving a couple of draw calls, unlike the HISM. So we get 19 instead of 21 mesh draw calls due to having a single LOD. However, there are more polygons for the GPU to render. Usually the extra draw calls in HISM are worth the performance increase on the GPU side, but in the end it's up to you to decide which trade-offs are appropriate for your situation. Here's an example of using spline meshes in a Super Metroid / Mega Man-like prototype we've been working on. As you can see, the majority of the level is built using the spline meshes rather than individually placing blocks. So let's see here, we have a floor, and in it I also added something to define what the mesh is, central wall, floor, or as a wall or floor from another level. I can change it to a wall, and it will immediately appear as such, but notice that the anchoring is set to match with the floor. And if I pick the ceiling, it will be on top. So if you have meshes that are set up this way, then you don't have to continuously reposition them every time. So I'm going to make a little copy here, holding the Alt key, and wall. Let's make another copy, and ceiling. And I basically have a corridor from a side view, fully done in 3 clicks. Thanks for watching. What method would you use? Let us know in the comments below. Please like and subscribe for future videos. And finally, consider supporting us on Patreon for exclusive content and other perks. See you in the next one.